According to the Bayes rule, to compute the posterior probabilities of specific parameter values, we need to take the prior probabilities of those parameter values, multiply them by the likelihood associated with those parameter values, and divide this product by the sum of such products across all the possible values of that parameter. These computations may be quite easy when we have only one parameter and only a few possible values of that parameter. Such computations become much more complicated when we have continuous distributions of parameter values and we have a large number of parameters. In such cases, doing calculations by hand may be prohibitively costly. And so, this is where the computational approaches, the computational methods come to rescue. One of the most typically used computational methods for computing the posterior distribution is called the Markov chain Monte Carlo approach. Without going into the details of how MCMC works, let me briefly outline the logic behind it, the process behind it. To run Markov chain Monte Carlo, the computer or the user picks a point in the parameter space, a particular combination of parameter values. Then the user or the computer specifies a rule according to which we should move from that particular point in the parameter space around the parameter space to a different point in that space. The computer, the sampler, repeats that operation many times, and at some point the distribution of the points in the parameter space visited by the sampler is no longer dependent on the initial values, the points where we started our journey. Now it has been shown that the distribution of the points in the parameter space visited this way converges to the posterior distribution that we are using to determine how exactly we are moving around the space. The outcome of running MCMC can be summarized using a table that contains a list of randomly drawn values from the posterior distribution. Here on the screen you can see 7 first rows from a hypothetical table with the randomly drawn values from the posterior. Typically this table would have much more observations, and this table would have a larger number of parameters. Now once you have such a table, you can use it to produce the summaries, to produce the estimates for your parameters, to capture the uncertainty that you should have about those estimates, and to compute all sorts of commodities of interest that depend on the parameters in the model. There are a number of different standalone programs used for running MCMC. Here is a short list of such programs. They include Bugs, WinBugs, JAX, OpenBugs, most recently Stan. Typically, when you use such programs, you use them in ensemble with some sort of data handling program. Typically, you would start with R, use R to prepare your data set and to feed the data and the model into those standalone programs. Once the program is done running MCMC, it will return the draws from the posterior distribution to R, and then you can work with them using R. There are a number of packages, R packages that are designed to make Bayesian analysis easier. Here is a shorter list of those packages. These packages would allow you to specify Bayesian models command style, that is, without writing out the likelihood function and the priors directly. Here I want to focus on one of these R packages, specifically on the package called rstanarm. This package was developed by the STAN development team, and this package relies on the STAN implementation of the Hamiltonian Monte Carlo for the estimation. This package includes a number of commonly used frequentist models: linear model, generalized linear model, multi-level models. And in order for you to be able to use these commands, you simply need to know the syntax for the corresponding frequentist function. If you know how to use the LM function, you know how to write a simplest version of the syntax for STAN LM. If you know how to estimate a logistic regression using GLM, you also know how to estimate a Bayesian version of a logistic regression using STAN GLM. Now, this package also has a bunch of utilities that can be used to summarize your posterior distributions and perform some predictive checks and some diagnostics on your estimates. As an exercise, I suggest that you use this package to estimate a logistic regression. Here's an outline of the steps that I want you to perform during this exercise. As the first step, please load the file turnout for logit.r data. This file contains a data frame called individual with the information from the 2008 general election in Canada. This file is based on the 2008 Canadian election study, but has much fewer observations and much fewer columns in it. At the second step, please use the GLM function to estimate a conventional logistic regression using maximum likelihood estimation. I would like you to use the variable called voted as your dependent variable. This is a binary indicator of turnout. I want you to use the variables called interest, knowledge, high school, and BA degree as the independent variables. Once you have successfully run this estimation, you will have a version of syntax that can be used for running logistic regression with MLE, and because of the ease of use of rstanarm, you will also have a version of syntax that can be used for computing the estimates for logistic regression using Bayesian estimation. At step 3, please load the rstanarm package, and at step 4, please run the STAN GLM function using the similar syntax to the one that you used in GLM. You can also look at the documentation for this function if you want to experiment with the priors and see what else this function can do for you. Once you have run this function, you are going to get a set of estimates. Now, as the next step, I want you to examine the priors that we used in the analysis. And to do that, you can use a prior underscore summary function on the object produced at step 4. The output from this function is going to be a list of the parameters that have prior distributions, alongside with the prior distributions used for those parameters. Please take a look and see which parameters have prior distributions and how exactly those prior distributions were specified. At step 6, you can use the function called sDataFrame to extract the random draws from the posterior distribution from the object created at step 4. This should give you a table with the draws from the posterior distribution. Once you have this table, you can go ahead and take a look at this table and generate all sorts of summaries for the posterior distributions. Draw them using histograms, generate the point estimates by applying the mean function or the median function to each of the columns, and generally look at the amount of dispersion in this table.